Welcome to Chapter 14, Neural Networks Fundamentals. Here we meet the model behind so much of modern AI, and we build it up from its simplest pieces with concepts, methods, and Python practice. Think of a phone transcribing your speech, a camera translating a foreign menu, or a photo app sorting pictures into people, pets, and places. Behind these feats sits a neural network, and it is far less mysterious than the headlines suggest. By the end of this chapter, you should be able to explain in plain language what an artificial neural network is, describe the roles of neurons, weights, biases, and layers, and understand the perceptron and why nonlinear activation functions matter. You should also be able to trace how forward propagation turns inputs into a prediction, state what a loss function is for, and grasp the intuition behind gradient descent, the learning rate, and backpropagation. This figure shows a multi-layer perceptron with one hidden layer. Every edge is a learnable weight. Each neuron applies a nonlinear activation to its weighted inputs, and backpropagation adjusts all the weights to make the network's outputs better. So what is a neural network? It is a model built from many small units called neurons, connected in layers. Each neuron combines its inputs with adjustable weights, applies a simple nonlinear transformation, and passes the result onward. The name borrows loosely from biology, but you need no neuroscience to understand the model. That single mechanism turns out to be flexible enough to power a remarkable range of tasks. Those tasks include classification, such as labeling spam or sorting images, regression, such as predicting a price or temperature, image, speech, and text recognition, and recommendation systems, and more recently, generative AI. The reason neural networks matter is that they learn complex, nonlinear relationships directly from data, the kind of relationships that resist tidy, handwritten rules. The story begins in the late 1950s with the perceptron, a model so simple you can compute it by hand. It first forms a weighted sum of the inputs, where each weight says how much that feature matters and a bias shifts the decision boundary. The perceptron generalizes naturally into the artificial neuron, the basic unit of every neural network. The neuron takes a weighted sum of its inputs, adds a bias, applies an activation function, and produces an output. A single neuron is still just a weighted vote. This figure shows one artificial neuron at work. Each input is multiplied by its weight. The products are summed together with a bias, and the total passes through an activation function to produce the output. Weights and biases are the parameters a network actually learns. A weight measures the strength and direction of a connection. In this respect, a neural network is a cousin of the linear and logistic regression models from chapters 6 and 7. Neurons are organized into layers. The input layer holds the raw features. One or more hidden layers transform the data step by step, and the output layer produces the final prediction. A network with at least one hidden layer is called a multi-layer perceptron. Activation functions are what make depth worthwhile. Without them, a stack of layers would collapse into a single linear transformation. A few functions appear again and again. The historical step function, the sigmoid that squashes inputs into 0 to 1, and tanh centered at 0. Two more functions complete the toolkit: RealU, the default choice for hidden layers in modern networks, and softmax, used in the output layer for multi-class classification. Different functions suit different jobs. This figure draws the three activation functions you will use most on common axes. Sigmoid squashes inputs into 0 to 1 and tanh into -1 to 1, but both saturate for large inputs, which weakens the gradients in deep networks. The sigmoid function maps any real number into a value between 0 and 1. Its S-shaped curve fits binary classification naturally, since the output reads directly as a probability. It does, however, have a well-known drawback. ReLU stands for Rectified Linear Unit, and despite the name, it is the simplest function imaginable. If the input is positive, it passes through unchanged, and if it is negative, the output is zero. That plainness is exactly why ReLU dominates modern hidden layers. The softmax function is the standard choice for the output layer when a model must pick one class out of several. A handwritten digit classifier is the textbook example. Forward propagation is how a network turns inputs into a prediction. The features enter the input layer. Each hidden layer computes weighted sums and applies an activation, and the output layer produces the result, flowing forward layer by layer. Continuing that flow, the output layer takes the hidden activations, forms its own weighted sum with a bias, and applies a final function to give the prediction. That completes one forward pass through the network. To improve, a network must know how wrong it is, and that is the job of the loss function. For regression with a continuous target, the usual choice is the mean squared error, which penalizes large mistakes heavily because the errors are squared. Once we have a loss, training becomes optimization. Find the weights that minimize it. We start from random weights, measure the loss, find how it changes with each weight, nudge each weight in the direction that lowers it, and repeat many times. The size of each step in that process is set by the learning rate. This figure shows gradient descent on a one-dimensional loss curve. From a random starting weight, each update steps downhill toward lower loss, and the steps shrink as the slope flattens out near the bottom. Gradient descent needs the gradient. For every weight, it must know whether nudging it up or down would lower the loss. The full training loop is a steady rhythm of 4 repeating steps. Those 4 steps are: forward propagation produces a prediction, the loss function measures the error, backpropagation computes how each weight should change, and gradient descent applies those changes. Run this loop over and over, and the weights drift toward values that make good predictions. This figure pictures the training loop. Each epoch runs a forward pass, computes the loss, backpropagates to obtain the gradients, and updates the weights, repeating until the model converges or reaches a maximum number of epochs. The 4-step loop sounds abstract until you push a single example all the way through it. Our tiny network has 2 inputs, one hidden neuron with a ReLU activation and one output neuron with a plain linear output, suitable for regression. This figure shows that tiny network used for the hand calculation, 2 inputs, one ReLU hidden neuron, and one linear output with 5 learnable parameters in total. We train on a single example with the first input equal to 1, the second equal to 2, and a target value of 2. On the backward pass, backpropagation assigns blame for the loss to each parameter by applying the chain rule, working from the output back toward the inputs. Gradient descent then updates the parameters, nudging each one against its gradient. The update rule is simple. Each parameter moves a small step opposite to its gradient, with the step scaled by the learning rate. For this example, we use a learning rate of 0.1. Notice that every weight moved up because every gradient was negative. The loss decreases as these weights grow, so that is the direction gradient descent takes. Now run the forward pass again with the updated weights, and the prediction comes out close to 1.985, much nearer to the target of 2 than before. One step of training already helped. Training rarely passes over the data just once. One complete pass through the entire training set is called an epoch, and networks usually train for many of them. The same flexibility that lets networks fit complex patterns also lets them overfit, memorizing the quirks and noise of the training data instead of the real signal. Happily, the toolkit for fighting overfitting is well stocked. The remedies include collecting more data, applying regularization to penalize large weights, using dropout to randomly switch off neurons, stopping training early, shrinking the model, and augmenting the data with transformed examples. Of these, regularization, dropout, and early stopping are the everyday staples of neural network training, and we return to all three of them in Chapter 15. Neural networks earn their popularity honestly. They learn complex, nonlinear patterns that simpler models miss, handle both classification and regression in one framework, excel on rich unstructured data like images, audio, and text, and form the foundation of modern AI. They also keep improving as more data becomes available, but they are not a free lunch. They typically need more data than simpler models. They can be expensive to train and tune, and they are harder to interpret than a linear model or a small decision tree. On top of that, they demand careful choices of architecture and training settings, and they overfit readily if they are not regularized. Here is the key point. A neural network is not always the right tool. On small or medium tabular data, logistic regression, random forests, and gradient boosting often match or beat it while being faster and easier to explain. Reach for them when the data is large, unstructured, or truly tangled. Let us see this in code. This example loads the breast cancer dataset, splits it into training and test sets, and builds a single pipeline that scales the features and then trains a multi-layer perceptron classifier. So, what does the code do? This network has two hidden layers, the first with 50 neurons and the second with 25, both using ReLU activations. Tabular data is a fine warm-up, but neural networks really shine on perceptual data like images. Let us turn to classifying handwritten digits. This code loads the digits dataset of small 8 by 8 grayscale images across 10 classes, splits it, and builds a pipeline that scales the pixels and trains a network with a single hidden layer of 100 neurons. With that single hidden layer of 100 neurons, this little network usually classifies the test digits with accuracy above 97%. Before trusting a model on images, it helps to see what the model actually sees. This short snippet uses Matplotlib to draw a small grid of the digit images, showing each picture together with its true label so we can inspect the raw data by eye. Remember that each picture is nothing but a grid of numbers, recording the brightness of every pixel. Consider a case study. A national postal service sorts millions of letters each day, many still carrying handwritten postal codes. It wants software that scans each envelope, locates the code, and converts the handwritten digits into machine-readable numbers for automated sorting. At its core, this is a multi-class classification problem. Each scanned digit must be assigned to one of the 10 classes, 0 through 9. A multi-layer perceptron handles clean, well-centered digits surprisingly well, and two practical lessons round out the story. The following Keras implementation builds the postal digit classifier from the case study, this time using the full MNIST dataset of handwritten digits. This code loads and normalizes the MNIST images, then builds a network with two hidden ReLU layers and dropout, ending in a softmax output over 10 classes. It compiles the model with the Atom optimizer and a cross-entropy loss, then trains it. This compact network routinely surpasses 97% test accuracy on MNIST, confirming that even a shallow, dense model can reliably read handwritten digits when trained on enough labeled examples. To summarize, a neural network is a stack of simple neurons connected by weights and biases and organized into layers. It learns through a steady loop of forward propagation, loss, back propagation, and weight updates, and we watch these ideas scale from tiny networks to industrial systems. For further reading, look to introductory machine learning textbooks, the scikit-learn documentation on the MLP classifier and regressor, deeper treatments of backpropagation, applied tutorials on digit recognition, and the original perceptron paper. Two further sources stand out. The landmark paper that introduced backpropagation for training multi-layer networks, and a comprehensive deep learning textbook covering the full range of architectures and training methods. That brings us to the end of Chapter 14, our introduction to neural network fundamentals.